Okay, so last time we discussed the limit of the complex balance functions. And today, so now this is time for the derivative or differentiation. So let me begin from the definition. I have a complex function f. This is a function which is defined on an open set containing a point z0 and the derivative of f at z0 is the limit by z minus z0. Also df dz at z0. Okay. And also we say if the limit of this guy exists, then we say f is differentiable at z0. F is said to be differentiable if okay, all right. So this is our definition, but this is not my favorite version of definition. Well, by just using change of variables. So if I setting the delta of z is z minus z0, I can rephrase the definition in another form like this. As z is tending to, delta of z is tending to 0, f of z 0 plus delta of z minus f of z0 over delta of z. So this is going to be our prime definition. Okay, all right. So as you can see from this definition, so there is actually no difference between the derivative of the real value function and the derivative of the complex values function. And exactly the same thing. So, but anyway, so as you can see from now on, so well, you will soon realize that there is a huge difference between the real derivative and the complex derivative. The complex derivative is actually more strict version of the real derivative. So that means, well, complex values function, it should be considered as a function from two-dimensional Euclidean space to two-dimensional Euclidean space. And even though you can actually see there are some functions which is differentiable in real sense, but at the same time that is not differentiable in complex sense. And you're gonna see the difference between these two in today's lecture. All right, so before I move on, so I will show you some small examples of the complex derivative. I guess this is the easiest one, the z squared. So what is the derivative of this guy? F prime of z is z is tending to 0 and z plus delta of z squared minus z squared and everything over z, delta of z. So this is what? So 2 times z times delta of z plus delta of z squared over. And so therefore, we have actually 2 delta of this on top of this fraction. So I can cancel these out. So it's 2 times z. So exactly the same as we expected from the real derivative. Just one more example. This time, I will say f of z is 1 over z. Then f prime of z is, well, this is very tedious computation. Should be 1 over delta of z and everything over z plus delta of z minus 1 over z. This is what? Yeah, actually, the result is the same as before, which is 1 over z squared, right? How do I know that? So the computation is very easy. So using the common fraction techniques, so you make these two guys, you have the same denominators. You multiply this guy by the top and bottom for the first fraction, you multiply by z and z. And for this guy, you multiply the top and bottom of this fraction by z plus delta of z. Then you have the two fractions with the same denominator. Then you know how to do this. So you cancel out the delta of z from top and bottom, and you put the delta of z equals to 0, then you will get the answer, which is negative 1 over z squared. So, I mean, the algebra is since the algebra is the same as in the complex real analysis, therefore this answer is also the same. Okay, so I don't want to spend too much time writing down the definition. It's easy properties, so I will just copy and paste some easy rules for the derivative. So these are the rules for the differentiation. So that is, if you take a derivative of some constant function, then the answer should be 0. And if you take a derivative of the power of z, so z to the nth power, then it's going to be n times z to the n minus 1. So as long as n is a positive integer. And also, the derivative is linear, and the product rule is also true for the complex derivative. And the quotient rule is also true. And the chain rule is also true for the complex derivative. So let me just take these rules granted, because, well, the proof is exactly the same as in the single valued real analysis. Okay. All right. Now, this time around, let me turn to some other non-examples. So which is differentiable in real sense, but which is not differentiable in complex sense. So these are some very interesting non-differentiable examples. which is the complex conjugate. So this is Z bar, so which is complex conjugate. So in other words, I can say f of x plus I y is x minus iy, right? So using the terminology from the multivariable calculus, I can say this function is actually x comma minus of y, right? So this is a function between from R2 to R2. So two-dimensional Euclidean space to another two-dimensional Euclidean space. And these are we say these are the component functions. These component functions are completely fine. They are just some degree one polynomials, which enjoys very nice properties. They are all continuous. They are all differentiable in infinitely many times. So in real sense, these are obviously some differential function, right? Okay, but things are different in complex. So according to our definition of the complex derivative, so we will need to consider this limit, z plus delta of z minus z, and I have to put the bar over here, and everything divided by delta of z, right? And the complex conjugate is linear. So I say z bar plus delta of z and everything bar minus z bar over delta of z, so which is just delta of z bar over just delta of over z. So now we are supposed to analyze whether the limit of this guy exists or not. And I want to claim that the limit of this guy does not exist. Why? There are many. There can be many explanations, but well, I will mainly stick to this explanation. So, well, you should be aware of that. This is actually a two-dimensional limit, right? So suppose that limit of this guy exists, then, well, and delta z is tending to 0. In this case, if the limit of this guy exists, then no matter which route do I choose, which is tending to the origin of the plane, then I am supposed to get the same answer for every route that I chose. So this is my plane of delta z, and my delta of z is tending to origin, which is this point. So therefore, I'm going to choose two different routes tending to origin. The first route, number one, is the horizontal route going along with the x-axis or the rear axis. And route number two, oh, sorry, I should choose the different color. And route number two, which is following the imaginary axis. Okay, so for the horizontal route, I will just say delta of z is delta of x comma 0. Suppose that I am following this route to the origin. Then this guy is following the horizontal route. So this delta of z is now delta of x tending to 0. And delta of z bar is delta of x plus I times delta of y, everything taken complex conjugate. This is my delta of z. But since on this route, delta of y should be 0, right? So therefore, this is just simply delta of x over delta over x. So the limit should be 1, right? On the other hand, if I choose to follow the imaginary axis, then then this delta of y should be tending to 0. And this time delta of x equals to 0. And since I am taking the complex conjugate, so this complex conjugate of delta of x plus I times delta of y should be delta of x minus I times delta of y. And here, since delta of x must be 0, so this guy, they just vanishes. They just vanish. And I have my minus sign over here and the positive sign on the bottom. And this imaginary unit I, they just cancel out each other. So what I have is just minus delta y over delta over y, which is minus. So, voila. So if I choose, I was able to find two different routes and both tending to 0. And taking the first route, it will going to give us the limit number 1. And taking the another route, it will going to give me the another limit, which is different from the first one. So which is clearly the evidence that the limit of this guy does not exist. Okay. Therefore, this complex conjugate function is not differentiable. Okay. What about this? Well, actually, precisely speaking, so this is not a complex values function, but this is a complex values function, but at the same time, this is a real values function. So this function is nothing but taking the modulus of the complex, the modulus of the input value, right? That's it. This guy is, well, as z is tending to 0, so f of z plus delta of z minus f of z over delta of z. Now I need to deal with this complex conjugate, modulus squared. And modulus squared is actually, in fact, just a complex number multiplied by its own complex conjugate minus z times the z bar and everything over delta of z. So this is okay. Oh, sorry. This complex I forgot to add the complex conjugate. So, but this complex conjugate can be broken down into these two. So Z times Z bar plus Z times complex conjugate of Z bar, delta of Z, sorry, and delta of Z times complex conjugate of Z plus delta of Z times delta of Z, everything conjugate, minus Z times Z bar, and everything divided by delta of Z. And well, these are some tedious algebra, but and these two guys, they cancel each other. And so eventually I have what? So these two guys, they cancel, and these two guys, they also cancel. So this is, yeah, delta of Z, sorry, Z bar plus delta of Z bar plus Z times complex conjugate of delta of Z over delta of Z. Okay, so I have just ended up with this some ugly expression over here. And what do you think of the limit of this guy? Exist or not exist? Let me see. The answer is depending on the value of the V, right? Well, more precisely, suppose if Z equals to 0, then this guy just vanishes. Therefore, I have very well-defined limit of this expression. But on the other hand, if Z is some non-zero complex number, then, well, inevitably, I will need to deal with the limit of this guy, and clearly the limit of this guy doesn't exist from the previous example. Therefore, this modulus function is complex differentiable only if at the origin, right? So, this modulus function is complex differentiable at Z equals to 0. I should say, sorry, only at the origin. Okay, yeah. So complex differentiability is far more strict condition than just real differentiability. So as you can see from these two examples, these are in real sense, in terms of the multivariable real algebra, this guy and this guy. So this is what? This is just x squared plus y squared, right? So these two functions, they are completely okay in terms of the real multivariable calculus, but in the complex analysis, so these two guys, they should be considered as a non-differentiable function, mainly because of the appearance of the complex conjugate. Okay, what about this? So suppose that some function is complex differentiable, then is it necessarily continuous at the point? What do you think? Yeah, actually that is true. So that is true. Well, the same proposition is also true in complex analysis. Well, if any function is complex differentiable at some certain point, then that function also must be continuous at the point. Why? Yeah. I know this is very silly, but well, I feel like I have to introduce this. If a function f is complex differentiable at z0, then it is continuous. The proof is not horribly complicated, but the proof is omitted. Okay. All right. Now I'm about to introduce you one of the most important criteria of complex differentiability, which is called the Cauchy and Riemann equation. Okay, now we know the real differentiable and complex differentiable, they are somehow different. Actually, and in fact, if some function is complex differentiable, then that function must be real differentiable. But you can always find some function, like just as we did in the previous examples. You can also find a function which is real differentiable but not complex differentiable. So therefore, it will be really nice that if we can find some conditions that tells us if any given complex values function is complex differentiable or not. If we can find such a nice criteria, then that is going to help us to determine if any given function is differentiable or not. The answer is the Cauchy and Riemann equation. Okay. What are these? Okay. We're going to talk about this in today's lecture. Well, first of all, Cauchy-Riemann equation is a necessary condition of being complex differentiable. But sooner, okay, it turns out that the Cauchy-Riemann equation is not only a sufficient necessary condition, but if some nice condition is imposed, then this Cauchy-Riemann condition is now being not only necessary, but also a sufficient condition for the complex differentiability. Okay. First, I will introduce why Cauchy-Riemann equations. I'm going to introduce the Cauchy-Riemann equations and why they are a necessary condition of being complex differentiable. Okay, so suppose that I have some complex differentiable functions. So I have this function. And as always, z is x plus I times y. But this is f of z is a complex number, so I can divide this guy as a real part and an imaginary part. And I'm going to write them like this. U x comma y plus I times v of x comma y. So u and v, they are both real values functions, and more specifically, u represent the real part of this function value, and v represent the imaginary part of the function. Okay, and since these two functions, u and v, they are both depending on the x coordinate and the y coordinate. So please allow me to write down like this: u of x and y, and v of x and y. Okay. All right. So and suppose that this guy is differentiable, complex differentiable at z equals to z0. I would say just z0 is the x and y coordinate, or real and imaginary part of the z0 to be x0 and y0. And delta of z is delta of x plus I times delta of y. Or sometimes I would just say x0 and y. And sometimes I would say delta of x comma delta of y. Okay, so since this function is differentiable at this point, therefore it is very natural to consider the limit of this quotient, f of z0 plus delta of z minus fz0, and everything over delta of z So, well, but since this function u consisting of the real and imaginary part, so u of x0 plus delta of x and y0 plus delta of y minus u x0 and y0 and everything over delta of x plus I times delta of y. So this is well, this represents the real part of the numerator, and plus for the imaginary part, I should have something like this. Almost everything just carries over, but u should be now v. Okay, so this is my difference quotient for the derivative. Okay. All right, good. And because of this assumption, because we are assuming that this function is complex differentiable at this point, the limit of this guy exists as delta of z is tending to 0, right? Okay, so that means, so this means, so well, say that this is my plane of delta of z. And delta of z is now tending to 0, tending to the origin. Therefore, if the limit of this guy exists, then that the same limit must be attained if I choose the horizontal path, right? And well, and since the limit of this guy exists, then I must be able to get the same limit if I choose to follow this vertical path, right? Because the limit of this guy exists. Okay, so first, let me try to choose the horizontal path, which that is tending to this, that is tending to 0. So the case number 1, I am taking the horizontal approach. Then, so to have the horizontal approach, then I have like then delta of z is delta of x plus I times delta of y. And since I am taking the horizontal approach, so therefore delta of y must be 0, right? And delta of x is tending to 0, right? This one is supposed to be the horizontal approach. Okay. Then delta of x equals to 0. I am taking the limit of this expression. I am taking limit of this expression, but now delta of y should be 0. So which is u x0 plus delta of x and y0 minus u x0 and y0. Everything over delta of x plus I times v of x0 plus delta of x and y0 minus v x0 y0 and everything over delta of x. Okay. Now what? Oh, this expression and that expression, they look very familiar to me. So this is actually precisely the definition of the partial derivative of the function with respect to x and y, right? So the first one is the partial derivative of u with respect to x at point x0 and y0, right? And plus I times the partial derivative of v with respect to x at the point x0 and y0. Okay. And this is the limit. And I claim that this limit must be the same as the derivative of function at point z0, right? Because this limit must have the exactly same value of the derivative of f at z0, right? Since we are assuming that function f is differentiable at this point. Okay. So I have very nice answer. So I have very nice result after this analysis because, well, if f is differentiable at some certain point, then the derivative can be written in terms of the partial derivative of the real and imaginary part of your function f, right? So if you can, in other words, if you can take the partial derivative of the real and imaginary part, then you can get the derivative at that point. Okay. Isn't that great? Okay. Okay, good. The next, this time around, instead of taking the horizontal approach, I will take the vertical approach to the origin. So taking the vertical path. So this time, delta of x should be 0, and delta y is tending to 0. And sorry, I will just copy and paste. So this time, delta of x equals to 0, and delta of y is tending to 0. So what? So u x0 and u0 delta y, u x0 and y0, and everything over I times delta y plus I times what I need to use, just replace u by v. Okay. Okay, all right. So yeah, the answer is, so almost similar analysis, but this time the only difference is I have this 1 over I factor in front of this guy, in front of this fraction. Okay. So times u, this is what? This is the partial derivative of function u with respect to y at x0 and y0, and plus, and I have I on the top and I on the bottom, so they cancel. So this is just the partial derivative of v with respect to y at x0 and y0. And sorry, I just changed my mind. I will just say just minus of I, right? 1 over I is the same as minus of I. Sorry, I changed my mind. Just one more time. I'm sorry about this. Because I prefer to have the real part first and the imaginary part later. So yeah, and by using the same logic, this number is also must be the exactly same number, which is the derivative of the function f at x is 0. So again, I get very interesting answer. So if you can do the partial derivative of your function in terms of y, then you can get the derivative, complex derivative at that point. Okay, now things are interesting, getting more interesting, because this number and that number, these two numbers, they represent the same thing, the derivative of the function f at z0. Therefore, these two numbers must be the same. So it follows that. Let me compare these two. No. Is so if two complex numbers are the same, then those two complex numbers must have the same real and imaginary part. Therefore, the partial derivative of x, partial derivative of u in terms of x is the partial derivative of v with respect to y, and partial derivative of v with respect to x is minus of the partial derivative of u with respect to y. Okay. So these two conditions is called the Cauchy-Riemann equations. So this is the first criteria that gives us the difference between the real and complex differentiability. So, well, that means even if your function is real different, even if your complex value function is real differentiable, but if it does not satisfy these two pair of equations, which is called the Cauchy-Riemann equation, if your function, if your function f fails to satisfy these two equations, then that is going to give the evidence that your function is not complex differentiable. Okay. So Cauchy-Riemann, so if you're following the logic, then you can easily convince yourself that these Cauchy-Riemann equations, they are actually not sufficient condition, but the necessary condition of complex differentiability. The Cauchy-Riemann equations alone does not guarantee your function is complex differentiable at that point. Okay, I'm going to show you some very interesting examples of this. First, a example, and second, the non-example. Let me consider this function, one of the easiest kind, which is z squared. And if we consider z to be x plus I times y, then this guy is x plus I times squared. So this is x squared minus y squared plus I times 2 times x times y, right? So for this function, the real part, u x comma y, is x squared minus y squared, and the imaginary part is 2 times x times y, right? Okay, now let me verify if these two functions satisfy the Cauchy-Riemann equations. And we now already know that these two functions, u and v, they must satisfy the Cauchy-Riemann equation because we know this function is complex differentiable. Okay. And yeah, this is very easy computation. Ux is 2 times x, and uy is minus 2 times y, and vx is what? 2y, and vy is 2 times x, right? So for every point, u sub x is the same as v sub y, and vx is the same as minus of u sub y. So these four functions, they are satisfying the Cauchy-Riemann equations. Okay. Okay. On top of that, so let me try to compute the derivative of this function. We already know the derivative of this function is 2 times z, right? But the same conclusion can be derived by using the Cauchy-Riemann equations. So we already know that if your function is complex differentiable, then according to the Cauchy-Riemann, according to the previous analysis, so this one must be the derivative too, right? Ux plus I times Vx. This one also must be the derivative. Or you can choose this guy. Okay, whatever. So, but I will take this expression. So Ux plus I times Vx, that is 2x plus I times 2 times y, right? And this is, simplifying this, I have 2 times x plus iy. But you know what? 2x plus iy is just z, so which is just 2 times z. So as we expected, the same conclusion can be derived by using this analysis. Well, or you can also verify this equality. Just try to use the v sub y minus I times v uy, and you can convince yourself that you'll get the same answer 2 times. Okay. All right. So the discussion so far can be summarized by this theorem. Suppose I have a complex values function, u plus I times v, is complex differentiable at this point. Then the first order partial derivative, the partial derivative, the u and v exist at this point, and they satisfy the Cauchy-Riemann condition. Is Vy x0 y0 and Uy x0 y0 is minus of Vx x0 and y0. So these are called the Cauchy-Riemann condition, or Cauchy-Riemann condition, or Cauchy-Riemann equations, and this is actually the necessary condition of the existence of the derivative at the point z0. Okay, now let me turn to this modulus function, which is z squared. And now let me try to decompose this function into the real and imaginary part. But this is very easy. So if writing down z as x plus I times y, then this function is just simply x squared plus y squared, right? And plus I times 0. So the function u is just merely x squared plus y squared, and v is just 0, right? So ux is 2x and uy is 2y, and the partial derivatives of v, they are all 0, right? And you have to note that you will need to observe that for these functions, the Cauchy-Riemann equation is only true at the origin, right? If you have spent some time working on the homework exercises, then you should be familiar to this function. So this is what? Am I right? Yeah. So if z is a non-zero complex number, then it's going to be complex conjugate of z squared divided by z. And if z is the origin, then the function value is equals to 0. So let me analyze this function. Well, so this guy, so divided by x plus iy. So, so please allow me to multiply the complex conjugate of x plus iy to the top and bottom of this fraction. Then I will just end up with x minus I times y to the third and over x squared plus y squared, right? So therefore, taking the real and imaginary part of this guy, this expression, so x to the third and minus 3 times x y squared. Am I right? Yeah. Yeah, and right, plus, minus 3 times x squared y plus y to the third. Okay, all right. So I have this is my real part of the function. And this is the imaginary part of the function, minus x squared y plus y third and x squared plus y squared. Wow. So I have two such ugly functions, ugly fractions. So yeah, I'm not going to spend too much time on verifying the Cauchy-Riemann equation. So I will leave it as an exercise. So why don't you try to find the first partial derivatives of these two functions and verify yourself that these two guys, they're satisfying the Cauchy-Riemann condition. But at the same time, so if you have seen your homework exercise, then you are supposed to show that this function is not complex differentiable at the origin. So this is very interesting example, such that even though this guy these functions are satisfying the Cauchy and Riemann conditions, but this function is not differentiable. So interesting. Okay. So it is easy to see that it satisfies Cauchy-Riemann equations, but not differentiable. Okay. So, well, so far, so we were discussing the Cauchy-Riemann equations as the necessary condition of complex differentiability. But but imposing some more nice conditions, then, well, I can prove that Cauchy-Riemann equations can actually be the not only necessary, but also sufficient condition of the complex differentiability. So this is what I'm going to prove for today's lecture. Oh. Okay, good. So the theorem goes like this. Good. F is, well, I have a function. So F is so U plus I times V. This function is defined on some, well, I should be saying the open neighborhood. But if I say neighborhood, then you are supposed to consider it open automatically. So, well, this guy is defined on some open neighborhood of a point Z0. And we are assuming these two conditions. So I have these two functions, U and V, and suppose that these guys are twice continuously differentiable on this entire neighborhood. And plus, also assume that these two functions, U and V, they are satisfying the Cauchy-Riemann conditions at this point. So differentiability at the neighborhood and Cauchy-Riemann condition at the point. Then, so well, basically, I am adding this one more condition. So then f prime of z0 exists, and its derivative is, as we expected, ux plus I times vx. So basically, I am adding just one more condition, twice continuously differentiable on the neighbor. Okay. So how can I prove this? Well, by using the Taylor's theorem on the multivariable functions. U x0 plus delta of x and y0 plus delta of y is so, and so the partial derivative of x times delta of x plus the partial derivative of u with respect to y and multiply by delta of y and plus the second order term. So this is going to be my remainder, 2 factorial over 1 over 2 factorial and times u xx x0 plus some constant between, so this data 1 is some number between 1 and 0, x y0 plus theta 1 delta y times delta of x squared plus 2 times u x y and the same thing times delta of x and delta of y plus u y y okay, and times delta of y, everything squared. No, sorry, not this. Squared and parentheses. All right, good. So this is the Taylor's theorem. So this theta 1 and sorry, this one should be theta 2. Whatever. So this is actually, this doesn't matter too much. So basically, so this is a degree 2 Taylor expansion of the multivariate function u at center at point x0 and y0, and so this is degree 1 term and this is degree 2 term, like this. So you can consider this as some kind of generalization of the mean value theorem. So you can find some numbers, theta 1 and theta 2 satisfy this equality. That's it. All right. Okay. Now, what I'm gonna do is these terms, they just carry over, but plus 1/2 of this guy plus I have 2 of these, and I will just take one of them. And I can get rid of this. And everything multiplied by delta of x plus 1/2. This time I need just, and since I have this, this one goes to here, and so I can rephrase like this. Okay. Then now what? So I'll just, so yeah, these are so ugly expressions, so I will just name it as epsilon 1. And for this guy, I will name it just epsilon 2. Okay. So a few remarks on this epsilon 1 and epsilon 2. So since my functions u, we are assuming that my function u was second continuously differentiable, right? So therefore, as delta of z, so which is just delta of x plus I times delta y, as delta of z is tending to 0, then so since delta of z tending to 0 means that delta of x and delta of y, they are simultaneously also they are both tending to 0, right? Therefore, these guys and these guys and these guys, they are also tending to x0 and y0, right? And since uxx and uxy, they are both continuous functions, that means these two second derivatives, they are completely well behaved and bounded near the x0 and y0, right? So I mean, they are both bounded. So therefore, these two numbers, they are bounded. So therefore, as delta of z tending to 0, this entire epsilon 1 should be also tending to 0, right? And the same is true for the epsilon 2. As delta of z is tending to 0, epsilon 2 also must tending to 0, right? Okay. So epsilon 1 and epsilon 2 is tending to 0 as delta of x and delta of y tending to 0. Well, we can apply the same trick for the function vx comma y. So likewise, we can find a function epsilon 3 and epsilon 4 such that vx0 plus delta x comma y0 plus delta y is vx0 y0 plus vx x0 and y0 delta x plus vy x0 y0 times delta y plus epsilon 3 delta x plus epsilon 4 delta y. And such that epsilon 3 and epsilon 4 goes to 0 as delta of x and delta y goes to 0. So we can find such 4 nice functions, epsilon 1, 2, 3, and 4. Okay. All right. Now finally, we are ready. Now we need to consider these different quotient. Z0 plus delta of z, comma, not this, minus f of z0, everything divided by, just forget about the denominator for a while. This is u x0 plus delta of x, y0 plus delta of y, plus I times v times this guy, and minus u x0 and y0 minus v, I forgot I times v of x0 and y0. So this is my f z0 plus z, delta z minus f of z0. So, okay, all right. Now I have to be extra careful. So this guy, so u x0 delta x, y0 delta y minus u x0 y0. So now let me go way back to the previous expression, which is simply this guy minus that guy, right? So, which is this guy minus this guy is this one plus that one plus epsilon 1 delta x plus epsilon 2 times delta y, right? So this is ux, not this, x0, y0, delta of x plus uy x0, y0, delta of y plus epsilon 1 delta of x plus epsilon 2 delta of y, and plus I times, well, same trick, this is should v and vy and epsilon 3 and epsilon 4. Okay. Now what? Yeah. And so far I'm just taking advantage of condition number 1. That is u and v are twice continuously differentiable. Now, this is time to make use of the Cauchy-Riemann equations. So since we are assuming that u and v satisfy the Cauchy-Riemann equations at this point, so therefore, using the Cauchy-Riemann equations, this uy should be, now let me replace this uy by minus of vx, okay? Now this is my vx. And for the second term, let me change vy by ux. Okay. All right, great. So I have what? ux x0 comma y0. So I am combining this term and that term plus delta x plus I times delta y and plus I times Vx x0 y0, and since I have here, so now this is, since this is minus y, but this is minus, but I should be saying this is plus I times delta y, I guess. Okay. Good. And plus epsilon 1 and plus epsilon 3. Sorry. I times epsilon 3, everything times delta x plus epsilon 2 plus I times epsilon 4 over delta y, right? Yeah. Great. So this is my f of z0 plus delta of z minus f of z0. Okay. Now, I want to divide this guy by delta of z. But you know, delta of z is simply delta of x plus delta of I times delta of y, right? So this is what? Just ux x0 y0 plus I times vx x0 and y0. You know, this guy and that guy, they just cancel with this denominator, right? And plus epsilon 1 plus I times epsilon 3 of delta x delta z plus epsilon 2 plus I times epsilon 4 of delta of y over delta of z. Great. And now we need to see that sorry. So let me just consider the modulus of this fraction. Which is just simply delta x over delta x plus I times delta y And for me, this is very obvious that this number should be always bounded by 1, right? Likewise, delta y over delta of z is also bounded by 1. And delta epsilon 1 plus I times epsilon 3 is because of the triangular inequality. And as delta of z is tending to 0, we know that this guy and that guy, they are both tending to 0. And delta epsilon 2 and epsilon 4 also tend, so as, okay, so what? So now if considering this difference quotient, as delta is tending to 0, this guy vanishes, since this is bounded by 1, this is bounded by 1, and this guy goes to 0, and this guy goes to 0. Therefore, the limit of this guy exists, which is equals to this. So therefore, the function is the complex differentiable at x0, y0. And this ends the proof. Okay, thanks for your patience, and I will see you on this Thursday. Thank you.